6 will be 30 questions. And number of questions will be 15. 15 into 2 will be 30. But questions will not become as 1, 2, 3, 4, 5, not like that. One question carrying 3 bits, another question carrying 3 bits, another question carrying 3 bits. Like this, there will be 6 questions. And each question, there will be either a small test or understanding, or a simple example, or a simple assignment question. Okay. Or a derivation type of simple derivation like derive work energy theorem. This type of questions will be asked. And out of this 30, normally what happens, 50%, because the mark will be calculated from 15. Suppose out of 30, you got 20 marks. So your sending will be done from calculated from 15 marks. So from 15, you will get 10. Like that, it will be done. And if possible, tomorrow in the next class, I will share 1 or 2 previous year questions also, so that you will have a idea about the type of the questions. Okay.
Yes, sir. Sir, how many chapters are going to come?
So all are problems.
No. Not all are problems. There
Is
will
any
be
theory?
there will be little amount of theory. Actually, the pattern should be like this: 30% will be knowledge, 30% will be understanding, and 30% will be applications. So applications mean problems. Understanding means test your understanding kind of questions, examples, and knowledge means little amount of derivations. Okay. Suppose you will be asked to derive Vx is equal to V naught x plus Vx square is equal to V naught x square plus 2ax into x minus x naught. Derive this equation. Then you will start and derive like this. Okay. Very simple, ordinary type of questions. If you understand physics, definitely you can answer those questions. And I will show 1 or 2 previous year questions, share those questions with you. You can take screenshot and we can also discuss. As far as the number of chapters are concerned, roughly 5 to 6 chapters are asked in the examination. But if let us assume that if the examination starts on 15th, then we have got lot of time. So I think at least I will cover another 1 or 2 chapters, because 6 is a very small chapter. Hopefully either it will be over today itself, it will be over. So chapter 7 will take few days, and then we may go to chapter 8. But I think up to chapter 7 questions may be asked, 6 or 7. That gradually will be very clear if things progress. However, what is the progress in other sections, on the basis of that, you can have a fair idea of that. Okay. I will share few earlier questions with you also. Okay. Is it okay?
Yes, sir.
Okay. So now we'll go to, so what did we do in the last class, where we left? Yes. Somebody of you just tell me where you left in the last class.
So example 6.2 done.
Example 6.2. So 6.3 we have not done.
No, sir.
नहीं ये so just wait. So 6.2 we have already completed, isn't it? 6.2. We have completed. Just let me share my screen with you. पुणे रैंक गुड़ाक okay. So 6.2 we have completed, isn't it, Sibun?
Yes, sir. 6.2 and test understanding.
Eh?
Understanding 6.1 and example 6.2 are completed.
Okay, example 6.2, test your understanding 6.1, that is over. So work energy theorem, have we started it or we have not started yet?
Not started.
Okay. So before going to test your understanding 6.2 and example 6.3, we will learn a new concept, that is what is called kinetic energy and the work energy theorem. Okay, so now we'll go to that thing, kinetic energy and work energy theorem. Now if you look at my screen, I have written kinetic energy and the work energy theorem. I will explain everything, just you look at this statement. Probably the black will be better for you, so let me make it black. So you see, the work done by the net force on a particle equals the change in the particle's kinetic energy. That is what is the theorem says. That means W total is equal to K2 minus K1. Okay, so first we will try to derive this equation for a constant force. Okay, so now look at the derivations. So I am deriving work energy theorem for a constant force. Work energy theorem work energy theorem for constant force. Okay, so for that what I will do, I will take a horizontal surface and I will think that there is a body moving with a velocity. I found that at t is equal to 0, a body is moving with velocity v1 in the forward direction, in the forward or in the positive x-axis, like this. Okay, then I apply a constant force, a pushing force. Okay, I pushes this moving body with a constant force F in the same direction, okay, as the body is moving, and in the process I was able to displace the body to a distance s. Okay, this distance is s. Or if the position of this body, this is at x1, if this is x1 and this position it is x2, then s is equal to x2 minus x1. S is equal to x2 minus x1. This is the change in position. Okay, and I find out that the velocity has changed at the position x2 and now the body is moving with a velocity v2. So naturally, because the velocity is changing, there is an acceleration, and I can find out the acceleration as rate of change of velocity. What is rate of change of velocity? That is change in velocity by change in time. So what is the change in velocity? The final is v2 the initial is v1. Okay, because the body is moving with a constant acceleration, so the average acceleration and the instantaneous acceleration is same. And this is suppose at time t, so t minus 0 is a t, isn't it? So this is its acceleration. I can also write this acceleration in another equations, which is vx square. I know that I have an equation like vx square is equal to v naught x square plus v naught x square plus 2ax plus 2ax into x minus x naught, x minus x naught. Okay, so but my vx is, I can change the symbol, my vx is v2, so v2 square is equal to, and my v naught x is v1, so v1 square plus 2ax and x minus x naught or x2 minus x1, I have taken it as s. So from here I will get the value of s. So what will be the value of s? S is equal to v2 square minus v1 square minus v1 square divided by 2ax. This is my s. Okay, so now because I have done work on this body by applying a constant force, in the process the body has displaced through a distance s, and the direction of force and displacement are along the same direction. So theta is equal to 0 degree or phi is equal to 0 degree, and w is equal to fs cos phi. I can write only w is equal to fs. Okay, so the work done is w is equal to fs. But according to Newton's second law, this F is equal to max, isn't it? So I can write F is equal to max. And then in place of S, I will put this value which I have just derived, V2 square minus V1 square. Okay, this is V2 square minus V1 square divided by 2 ax 2ax. So v2 square minus v1 square by 2ax. So this will be max, and this s is equal to v2 square minus v1 square by 2ax. Yes, this is right. In place of s, I have put this value. So what will happen? This ax get cancelled. So I got the value of my w as w is equal to half mv2 square, half mv2 square, mv2 square minus half mv1 square, m v1 square of m v1 square. So this is a very peculiar kind of result. If somebody has not known any physics or he is blank, which is better, then one can understand that the amount of work that I did on a body is equal to difference of two new quantities. So what is these new two quantities? What is one is half mv2 square and another is half mv1 square. So this is a very interesting result because you know what is a half mv square, so that you can say. But if somebody doesn't know, then he will be surprised to find that he is doing work on the body and which is equal to the difference of two new quantities. So what are those new quantities? Let us try to find out its identity or its exact characteristic features. Okay, so what I will do, let us, initially the body was at rest. Okay, if the body was initially at rest, then V1 is equal to 0. And if V1 is equal to 0, then there is no necessity of writing V2. I can write V2 as V, isn't it? So when you do W amount of work in a body, then you find out that your amount of work done on the body is equal to a new quantity which is called half mv square, and where this the presence of this v shows that the body which is moving has in it an energy, and that energy has an expression which is half mv square. So we can say that any moving body possesses an energy which is known as kinetic energy, and that kinetic energy can be written as 1 by 2 times the product of mass of the body and the square of the speed with which it is moving. So naturally, when you do work to a body, that work is expressed itself in kinetic energy. So once we are able to show that half mv square is actually kinetic energy, then I can interpret my half mv2 square as final kinetic energy and half mv1 square as initial kinetic energy. And as for initial, I write 1. I will write K1 is equal to half mv1 square, half mv1 square, okay, and K2 is equal to half mv2 square. So K1 is equal to half mv1 square and K2 is equal to half mv2 square. So now I get my equation as W is equal to, this W is equal to K2 minus K1, K2 minus K1, or that is also equal to change in kinetic energy, that is delta K. Okay, delta is for change, K is for kinetic energy. Okay, so the work you did on a body is equal to change in kinetic energy, isn't it? Is equal to change in kinetic energy. So if we go to the statement part of this equation, then you will see that that is what the equation says. The work done by the net force on a particle equals the change in the particle's kinetic energy, or W total is equal to K2 minus K1. And this is for constant force that we have derived. Now you can also rephrase this statement like this: the total work done by all the forces on a particle equals the change in the particle's kinetic energy. Because when you say net force, definitely all the forces are included in net force. So that's why you are writing work done means total work done. But when the total work done is not mentioned, and then or net force is not mentioned, you can rephrase this statement as the total work done by all the forces on a particle is equal to the change in the particle's kinetic energy. Okay, if you now will go to another example, example 6.3, where we can find an application of this work energy theorem. Now all of you know about the example 6.2, where that sled of 14,700 Newton was pulled by a force of 5,000 Newton, making an angle of 36.9 degree, and it was also experiencing a frictional force of 3,500 Newton. And then he was asked to find the total work done by the forces present. Okay, and how we have proceeded, if you have remembered, then I will just, because in order to do this example 6.3, I need the reference of example 5.2. So I will repeat example 5.2 and then we'll go to example 5.3. So what was example, sorry, 5, not 5, 6.2. So what was example 6.2? There was a sled of weight 14,700 Newton, and it was being pulled by a force of 5,000 Newton, making an angle 36.9 degree. this angle is 36.9 degree with the horizontal. So this angle is 36.9 degree. And this sled has a weight which is 14,700. This is 36.9 degree. And it has a weight which is 14,700 Newton. 14,700 Newton. This was the weight or mg. Okay, and also there is a frictional force acting which is 3,500 Newton. This F is equal to 3,500 Newton. And you are asked to find out the total work done. Okay, how you will do it? This is Newton and this is this Ft, because you are pulling through a rope. That's why I have mentioned T means tension. So this was 5,000 Newton. Because this force is not is inclined, it is acting at an angle of 36.9 degree. So only the parallel component will do work and the perpendicular component will not do any work. That you must understand. So F perpendicular will not do anything, F parallel will do work. So what will be the value of F parallel? Ft 36 cos 36.9 degree. That means the parallel component F parallel which will do work or which is along the positive x-axis, its value is Ft cos 36.9 degree. Cos 36.9 degree. Because 36.9 degree is 0.8 and Ft is 5,000, 5,000 into 0.8 is 4,000 Newton. So a force of 4,000 Newton is pulling the body in the positive x direction, and another force of friction which is pulling the body, in the opposite direction with another force of 3,500 Newton in the negative x direction. So one is a positive, one is directed along the positive x-axis and another is directed along the negative x-axis. So I have put a minus here. So what will be the net force? So the net force acting on this sled will be 4,000 Newton minus 3,500 Newton will be 500 Newton. And because this application, this force which is applied to this sled moves, the sled is displaced through a distance of 20 meters. So what is the amount of work done? So W is equal to, because it is a constant force acting along the same direction as the displacement, so just a simple multiplication of sum of all Fx into S. Okay, and I get 500 Newton into 20 meter will be 10,000 joule. Okay, so I will be getting 10,000 joule. So 10,000 joule of work is being done on the body. Okay, what will happen with this work? So if the total work done is 10,000 joule, then what will be the new kinetic energy? Because according to the work energy theorem, W total is equal to K2 minus K1. So K2 is equal to K1 plus W total. Okay, so let us find out K1 also. K1 plus W total. Okay, now this brings us to example 6.3 actually. So now we understand that if we apply work energy equivalence principle, then we will find out that the final kinetic energy is equal to initial kinetic energy plus the amount of work either done on the body plus, or if the work is done by the body, then minus, and if there is no work is done, then K2 is equal to K1. So now coming to this 6.3 example, 6.3 what it is telling, let us see. So 6.3 is telling that let us take the slide of example 6.2. Now suppose the sled was moving with an initial speed of 2 meters per second. What is the speed of the sled after it has moved to 20 meters? So what is the speed that we have to calculate? So the speed is, because K2 is equal to half mv, K2 is equal to half mv2 square, half mv2 square. This is K2, half mv2 square, and we are to find out V2. So what will be the value of V2? So V2 is equal to 2K2, 2K2 divided by M and then a square root. So this is my V2. And what is my K1? K1 is equal to half mv1 square, half mv1 square. And what is my m? Because mg is given, mg or the weight of the slate is how much Newton? 14,700 Newton. 14,700 Newton. Okay, 14,700 Newton. This is your mg. So what will be your m? M is equal to 14,700 divided by 9.8. So if you do the calculation, you will get 1500 kg. Okay, so this is 9.8. The upward is in Newton, this is in Newton, and this downward is in meter per second square. So naturally you will get in kg, and the value will be 1500 kg. So your mass of the slate is 1500 kg. Now put this 1500 in the above equation, in the K1 equation, because K1 is equal to half mv1 square. So that is equal to half into your mass 1500. Your mass is 1500, and then V1 square. V1 square is 2 square, because the slate is moving with 2 meter per second. So 2 square is 4. So I will get 3000 joule. So because the slate is moving at a speed, a slate of mass 1500 kg is moving at a speed of 2 meter per second before work is done on it. So once a 10,000 joule of work is done on this body, then its final kinetic energy becomes your K2 is equal to K1 plus W, K1 plus W total, isn't it? W total we have already calculated as 10,000 joule. K1 just now we have calculated it as 3000 joule. So K1 plus K2, 10,000, 3000 plus 10,000 becomes 13,000 joule. So 13,000 joule is of energy, kinetic energy is now possessed by the body. Now this amount of energy corresponds to what velocity for a 1500 kg body. Now we'll see by applying these equations that I have derived earlier, which was this equation V2 is equal to root over 2K2 by m. So I will take square root, write 2, then in place of k I will write 13,000, 1, 3, and there are 3 zeros. Okay, and divide it by mass, which is 1500, 1500. Okay, so you see 0, 0, 0, 0, then 5, 3, and here 26, isn't it? So finally you will get 26 into 2 is 52 divided by 3 square root. Okay, so roughly this is square root of 17. So it will be so the value will be somewhere between 4 and 5. So the exact value, if you do the calculation, will be 4.2 meter per second. So naturally, because the body has got this amount of energy from outside, so its kinetic energy will become 13,000 joule, and its speed will be 4.2 meter per second. So naturally we have applied the work energy theorem, and we can work out this problem and can predict that the speed of the slate has increased twofold, because earlier it was moving at 2 meter per second, and now it is moving double the speed, more than double the speed, with 4.2 meter per second. How that happened? Because the force that you are applying, that 5,000 Newton force, making an angle of 36.9 degree, you are able to have a force of 500 Newton still there, after balancing the 3500 frictional force, you are left with a net force of 500 Newton, which has displaced the body through a 20 meter and pumped 10,000 joule of energy into the body. That's why the body's energy becomes 13,000 joule and the body could speed up. So this is the logic. Now we'll go to one test your understanding and try to understand this work energy theorem in a much better way. Okay, so now I'll go to test your understanding 6.2. So test your understanding 6.2. So what is test your understanding 6.2? Let me write the test your understanding first, then we will do it. So test your understanding 6.2. Rank the following bodies. So we should make it black actually. Okay. Rank the following bodies in order of their kinetic energy. In order of their kinetic energy from least to greatest. From least to the greatest. Okay. And what are the options? A 2 kg body moving at 5 meter per second. Okay. And option 2, a 1 kg body that initially was at rest and then had 30 joule of work done on it. A 1 kg body that initially was moving at 4 meter per second and then had 20 joule of work done on it. And finally, a 2 kg body that initially was moving at 10 meter per second and then did 80 joule of work on another body. Okay, so we will first analyze this question. Okay, then before doing this question, let us analyze this question. Okay, we have to arrange the energy of these 4 bodies, kinetic energy of these 4 bodies in order of least to greatest. Though that body which possesses the least of kinetic energy will come first, and that body which possesses the greatest amount of kinetic energy will come last. So that is our idea. So we must first find out the kinetic energy possessed by each body in each bit of the question. A 2 kg body moving at 5 meter per second. How much kinetic energy this body contains? Let us see. So a 2 kg body moving with 5 meter per second. Okay, so we'll apply half mv square because the body is probably moving with constant velocity. Okay, so its speed is remaining same, so the kinetic energy will also remain same. So K1 is equal to K2. So let us calculate K1. So K1 is equal to half mass of the body into speed of the body square. And it's a scalar quantity. Its unit is joule. So half mass is 2 kg and velocity is 5 meters, 5 square. Okay. So this 2 get cancelled. You get 25 and the unit is joule. So K1 or which is also equal to K2. So K2 means final kinetic energy, that is equal to initial kinetic energy, and that is equal to 25 joule. So this is the answer for the first bit of question. Okay. Now we'll go to the second bit of question. So what is the second bit of question? Now the second bit of question says that a 1 kg body that initially was at rest and then had 30 joule of work done on it. So this body was initially at rest. So K1 is equal to 0. Because it was at rest, no speed. So K1 is equal to 0. So this is 1 actually. I am doing test your understanding. Test your understanding 6.2. Test your understanding 6.2. And how much work is done on the body? 30 joule of work is done on the body. So K2 will be W total. First let me write W total is equal to 30 joule. And we have to find out what is K2. K2 is equal to K1 plus W total. K2 is equal to K1 plus W total. K1 plus W total. Because K1 is equal to K1 plus W total. K1 is equal to 0, W total is equal to 30 joule. So K2 is equal to 30 joule. So the second bit will give us K2 is equal to 30 joule. That is also equal to K1. Okay. And third, let us see third. A 1 kg body that initially was moving at 4 meters per second and then had 20 joule of work done on it. Okay. So the body was moving with 4 meters per second and 20 joule of work, 4 meters per second. So if the body is moving with 4 meters per second, so what should be its kinetic energy? So let us find out first. Okay. So what will be its kinetic energy? The kinetic energy K1 will be half mv square. So what is the body? 1 kg 4 meters per second. 1 kg and 4 meters per second square will be 16 meters square per second square. And so what is its mass? Just wait. A 1 kg body that initially was moving at 4 meters per second and then had 20 joule of work done on it. Okay. So initially its kinetic energy is 8 joule. Then it received this kinetic energy in the form of work. So W total is equal to 20 joule. So naturally its kinetic energy will increase and the new kinetic energy of this body will become 20 K2 is equal to K1 plus W total is equal to 28 joule. So now the body possesses 28 joule of kinetic energy. So in bit 3 we will write K3 is equal to 28 joule. Okay. So now we'll come to the last part. In the last part, what is happening? A 2 kg body that initially was moving at 10 meter per second and then did 80 joule of work on another body. So what is actually happening now? This body is moving with a very high speed, 20 meter per second, sorry, 10 meter per second. So it will possess a lot of kinetic energy, because probably it possesses a lot of kinetic energy. So it will do work on another body, and what will happen, let us see. So, sorry, I am not getting. What did I did? Have I taken the brush? Oh, sorry. Okay. So what I did, now mass is 2 kg moving with 10 meter per second. Okay. So the kinetic energy K1 of the body is equal to half mv1 square. So half mass is 2 kg. So 2 and moving with 10 meter per second. So its square will be 100 and the unit will be joule, because I am dealing with K1. So from here you will get the body possesses a lot of huge amount of kinetic energy, 100 joule. And it did work. It spent energy from its own pocket, and work is now done by this body on another body. Work is not on this body by another body, but this body does work on another body. So I will put a negative sign, and my W total is minus 82. So what will be K2? Now K2 is equal to K1 plus W total. K1 plus W total. Okay. So K1 is how much? Is 1000 joule. Sorry, 100 joule. And this is 80 joule. So 100 minus 80. Okay, this is joule. So let me write a joule. And finally I got 20 joule. Okay, so the first bit was 25, second bit was 30, third bit was 28 joule, and the fourth bit, oh sorry, all these are K2, not K3. So this K2 is equal to 20 joule. So now I have to arrange them. So which is the least value? So fourth is the least value. So the arrangement will be first 4, then the next value will be 25 joule. So 1, and then the next value will be 28 joule. So third, and finally the maximum value is 30 joule. So it will come last. So this is the arrangement, isn't it, of this test your understanding. So this is 6.2. Now we have worked out the work energy theorem for a constant force. So naturally you will ask me a question, what will happen if the force will change, if the force will not remain constant? Then can the work energy theorem be valid or not? Can we get the same form of the work energy theorem? This is our next question, or okay, our next topic. So work energy theorem for a, what is happening? So work energy theorem for a varying force. Okay. So work and energy with varying forces. This is topic 6.3. 6.3, work and energy with varying forces. Work and energy. Work and energy for varying forces. Work and energy for varying forces. For varying forces. So work and energy for varying forces. What will happen? Before that, let me ask you a question, and then we will simulate that question with this topic. Let us say that I will take a body. A body is moving horizontally. Suppose at this point you find out the speed to be 5 meter per second. Okay, and after 4 seconds of motion, you find out that the same body after 4 seconds is now moving with a speed of 8 meter per second. Now I will ask you to find out the distance traveled by the body in 4 seconds. Because in 4 seconds, the body's speed changes from 5 meter per second to 8 meter per second. Okay, then how much distance the body has traveled in this 4 seconds? So that is the problem. So how we are going to solve that problem? Okay, first let us do I will ask you a few questions, and then we will do this problem, and then we will go to the varying forces problem. Now suppose I will say that the body is moving, the body has covered 5 meter per second into 4 second, second cancel 20 meter. Will I be right or wrong if I say that the body has traveled 20 meter in 4 seconds? Am I correct or am I wrong? Yes, any one of you? Asutosh, and there are only 58 students probably. Many of you have 62. Okay, so what will happen? Yes, what will happen? Will it travel 20 meter? If the body is traveling with a speed of 5 meter per second, and am I audible? Am I audible?
Yes, sir, audible.
Audible. Then you just say, suppose the body is traveling with a velocity of 5 meter per second and it travels for 4 seconds, but at the end I found out that the body is now not traveling with 5 meter per second, the body is traveling with 8 meter per second. And during this 4 second, continuously the speed of the body has increased, and so I want to find out the distance traveled by the body. So I know that distance is equal to speed into time, and I thought that maybe that will be correct. So I multiply 5 meter per second with 4 second, and I got a value 20 meter. Now my question is it correct or will it be wrong?
So it is wrong.
That is wrong. So I thought that probably that will be wrong, because maybe I have taken a very small value of this speed. So why not go for 8 meter per second? Then I multiply 8 meter per second with 4 second, and I got another value, that is 32 meter. Now will I be correct or again I will be wrong?
Wrong, sir.
I will be again wrong, because if I write 20 meter, I will be less than the actual value. If I write 32 meter, I will be above the actual value, because because the actual value lies somewhere between 20 to 32. Then I thought that why not take an average? So I take an average velocity, like I add these two velocities, 5 plus 8. Actually, the average velocity is calculated not in this way. The average velocity is calculated by taking the total distance traveled divided by the total time taken. That will give you the average velocity. But I thought that there was an initial speed of 5, final 8. So 8 plus 5 will be 13, divided by 2 will be 6.5 meter per second. So where should I take 5 meter? Where should I bother 8 meter? Let us take 6 meter per second and multiply with it with 4 second, and then I will be getting a value which will be between 20 and 32. So I will be getting a value that is 4 into 6 is 24, and 0.5 into 4 is 2. So 26 meter. So okay, 26. Will I be correct? If I
Yes, sir. Correct.
I will be correct. I will be correct. So let us check whether I am correct or not. I know little amount of kinematics. Okay. So what I will do, I will first find out the acceleration of the body. So how I will find out the acceleration of the body? Final velocity minus initial velocity, 8 meter per second minus 5 meter per second will be 3 meter per second, isn't it? Then I will divide it by 4 seconds, because this 3 meter per second change in velocity has taken place in 4 seconds. So what is the per second change? Then the per second change will be 3 by 4 meter per second square. 3 by 4 meter per second square. Then I use the formula that x is equal to x naught, x is equal to x naught plus v naught xt plus v naught xt plus half axt square plus half axt square. So this is the formula, and I want to apply this formula and find out the distance traveled by the body. Because x naught is my choice, it depends upon my choice. I take my origin at 0, 0. So at t is equal to 0. Suppose the body was at 0. So this is 0. So what is v naught x? The initial velocity is 5 meter per second into t is 4 seconds. So 20 meter. 5 into 4 is 20 meter. This 20 meter, you see. But now the body has also traveled an extra distance due to this acceleration. And what is this extra distance? Half into ax is 3 by 4. This is 3 by 4 into t square is 16. So the denominator is 8 and the numerator is 48. So I will get 6 meter plus 20 meter is 26 meter. So I am right. Actually, earlier also I thought that it should be 26 meter, and now my rigorous physics also tell me the same thing, that the body must have covered 26 meter, extra 6 meters, isn't it? So this is how also, suppose now I will the same thing. Now you just look at this same problem. Now I will just change this 5 meter per second as 5 Newton. I will just make it 5 Newton, isn't it? I will make it 5 Newton, and this is, I will make this 8 meter per second as 8 Newton. So what I will try to say you that when the body experiences first a force of 5 Newton, and finally because the force is continuously changing after a distance of, and this second is, suppose now I will replace this second by meter displacement. Okay, the whole thing now the same concept is same, only I am changing the terms. So now what is happening? Now initially the body experiences a force of 5 Newton, and in the process the body gets displaced through a distance of 4 meter. But at the end I observe that the force is not 5 Newton, but it is 8 Newton. So if I say that the body has, if I say that 20 Newton meter, or that is what is joule, 20 joule of work is being done on the body, then I will be at the lower side of the error, isn't it? And if I say that 32 joule of work has been done on the body, then I will be at the higher side of the error, because by taking 20 joule, I will commit a mistake, because I should be a little bit more, but I am quoting a low value. If I take 32 joule, then I am on the higher side of the error. I should have been little bit smaller, because the value lies somewhere between 20 to 32, isn't it? So now how we are going to solve this problem? That is very important. So what I should do exactly in the same way, maybe let us find out, I don't know, let us find out maybe a 6.5 into 4, that means 26 joule work might have been done in this process, because isn't it? So I will be getting 26 joule. So what is happening? Let us see what we are going to get. Because you see, so what I will do, I will divide this 4 meter, this big interval, this big displacement into very small one. isn't it? But like this very small one, very small one. So why I am dividing this 4 meter into small? I know that my force is not remaining constant over this 4 meter distance. But if I take a very small distance, infinitesimally small, then maybe I can use my 5 Newton, isn't it? I can use a constant force. Maybe the force is changing over a long distance from 5 Newton to, the change is not sudden. The force is changing from 5 Newton to 8 Newton over a distance, over a displacement of 4 meter. So if I take a small displacement, then maybe I will argue that the force is remaining constant over that small distance. So my small amount of work I can write is as force, constant force over the small displacement dx. So that will give me my small amount of work dw. And I will add all this dw and I will get my w. So my w will become, what will be my w? My w will be integration, that is a summation of a continuous term. So it is almost like a sum, okay? So of dw, or that dw is equal to sum of from x1 to x2. What is the displacement of the body from x1 to x2? F dx, isn't it? F dx. Okay, because this force is not constant, so I am writing F dx. So in the next class, I will show you that we have calculated this 26 joule, and the mathematics, what the mathematics is giving us, we will see. Because now we will find out that the W will not look like Fs, but now the W is equal to integration of x1 to x2, isn't it? F dx. It will look like this, isn't it? And from there, we will go to the work energy theorem, whether we are getting that W is total is equal to K2 minus K1 or not, that we will see. So I think I should stop here. Is it okay?
Yes, sir.
Okay. So
Yes.
I am stopping here. Thank you very much for your attention, and we will meet in the next class. Okay. Thank you.